In the previous video, we've seen the games that have saddle points. In those kind of games, once we found the saddle points, then all the players, two players, need to stick to that optimal strategies all the time. So they always have to play that strategy. Anybody who moves away from that strategy will experience losses. Okay, but we've also talked about there are some games that do not have saddle points. For those kind of games, it means that we need to have a different type of strategy, and that is called the randomized strategy. So let's start. Here's an example of a two-person zero-sum game that does not have a saddle point. So the game is like this. Two players, let's call them odd player and even player, simultaneously choose the number of fingers, one or two fingers, to put out. If the sum of the fingers put out by both players is odd, then the odd player wins $1 from even. However, if the sum of the fingers is even, then it is even player who wins $1 from odd. So this is the reward matrix. Let's see an example. If the odd player puts out one finger, and then the column player also puts out one finger, the sum of 1 and 1 is 2. So the winner is the even player. That's why it is called -1, because in this matrix the reward is always with respect to row player. In other words, this -1 means that the odd player loses $1. On the other hand, the column player wins $1. Suppose the row player puts out two fingers, but the column player still puts one finger, so the sum of the fingers 2 plus 1 is 3, and 3 is an odd number, so here the reward for the odd player is +1. So the odd player wins $1, or in other words, the column player loses $1. Okay, so the question is we need to determine whether this game has a saddle point. Well, we can tell that the game has no saddle points because the requirement for saddle points is that the maximum of the row minimum must be equal to the minimum of the column maximum. So here we can see that the maximum of the row minimum is -1, while on the other hand the minimum of the column maximum is +1. So -1 does not equal to +1, so we do not have a saddle point. That's from the formula. But we can also think about why this game does not have a saddle point by looking at the pairs of strategies. So for example, if the odd player puts out one finger and then the column player also puts out one finger, then the row player loses $1. So in this case, the row player may say that let me switch the strategy to become two fingers, right? Because now if the row player puts out two fingers, now it wins $1, which is better. But then once they are in this situation, the row player plays two finger, column players play one finger. Now the column player may think that, okay, let me switch to the other strategy. Let me switch to two fingers. Because now if this pair of strategies happens, then the column player wins $1. But then you can see the row player can say, let me switch back to one finger, because this gives me the win of $1. Now in this situation you can see that the column player may say that let me switch back to one finger, and then so it keeps going on and on and on, that one player can switch his or her strategy, and then he or she gain benefit by changing the strategy. You can see that this is different with the case when saddle point exists. When the saddle point exists, none of the player may obtain any benefit from switching from the optimal strategy. They always need to stick to their optimal strategies in the game that has saddle points. Here, on the other hand, we don't have any pair of strategies that is stable. Okay, for any choice of strategies by both players, it is said here, there is a player who can benefit by unilaterally changing the strategy. So they will always keep changing strategy. Nobody can just stick to one strategy, because anybody who just stick to one strategy may experience loss because the opponent may just move to the other strategy. So this is the case where we don't have a saddle point. So to summarize the difference, when the game has a saddle point, we have a pure strategy. It is called pure strategy because each time the player must play the same optimal strategy. Nobody can switch, nobody can change. Okay, that's the game with the saddle point. But the games without saddle point, we need a mixed or randomized strategy. In other words, we need to have a decision variable to say the probability that odd plays the first strategy. And then also another decision variable to say that this is the probability that odd plays the second strategy. Similarly, for the column player, the even player, we need to have decision variables. For example, y1 denotes the probability that even puts out one finger, and y2 denotes the probability that even puts out two fingers. Of course, the sum of these probability x1 plus x2 must be 1, and then y1 and y2 must be 1 as well. Since we only have two variables, x1, x2, and also y1, y2, we are going to do the graphical approach to find the solution. Let's start by imagining us as a row player or the odd player. If we are the odd player, we cannot control what our opponent will play, right? We do not know what the even player will play, what kind of strategy the opponent will play. We do not know that, and we cannot control that. So we may just compute our expected reward by thinking if column player plays one finger and if column player plays two fingers. The word if here again, because if we are the row player, we cannot control whatever the column player will do, right? So the row's reward, if the column picks one finger, the row player will get -1 if the row player plays one finger. So -1 if row player plays one finger, and then +1 if row player plays two fingers. So this -1 is if the player plays one finger, and the probability is x1. This +1 is if the row player plays the strategy of two fingers, which is x2. So the expected reward for a row player, if the even player plays one finger, is -1 x1 plus 1 x2. Similarly, we need to compute if the column player plays two fingers. We will get +1 if we play one finger. We will get -1 if we play two fingers. Now these are the probability of we, the odd player, playing one finger and two fingers. So these are the expected reward for rows with respect to if column plays one finger and if column plays two fingers. Again, we separate these two conditions if column player picks one finger and if column player picks two fingers, because again, we as the row player cannot control whatever strategy that the column player will play. Now let's draw the equation of the expected rewards. If even player picks one finger, we have seen that this is the expected reward for row player. So let's denote the row's reward with y, and then we replace x2 with 1 minus x1, because the sum of probability of x1 and x2 must be 1, so we may replace x2 with 1 minus x1. So we obtain the equation y equals minus 2x1 plus 1, and that is this line, AC line. This is point A and this is point C, and the line shows the expected reward for row player if even picks one finger. Similarly, if even picks two finger, we may draw the row's reward, and then it is the line of D and E. Now, because this is the expected reward for odd player, so the even player will always try to do something that makes the row player receives as minimum reward as possible, right? So for example, if this is the value of x1 here, even player will pick 2, because if the even player picks 1, it will give a high reward to the row player, and the column player does not want to do that. If x1 is over here, then the even player again will pick the one that minimizes the reward for the row player. So the reward for row player will always be this part of the lines, okay, because the even player will always try to minimize the reward for row player. So the best that the row player can do is at point B, which is half, right? You see that these are all the possibilities of the reward that the row player may receive, and the best that the row player may do is at point B, which means x1 equals 1 over 2. Now let's take a look at this game from the side of the column player. So again, if we are the column player, our reward depends on the row's choice, and we do not have any control for the strategies that the row player will play, right? So same as before, we compute the reward if row player picks one finger and the row player picks two finger. But then we still compute the row's reward because all values here, they are about the reward for the row players. Okay, so for column player, we still compute the row's reward, but we want to minimize them. Okay, we do the same thing as before. So we cannot control what row player may do. So if the row player plays one finger, we receive -1 and +1. We receive -1 as the column player. If we play one finger strategy, the probability is y1. We receive +1 if we play two finger strategy, and then we play it with the probability of y2. So that's how we get this equation, and the similar idea apply to the second equation. Similarly, we are going to draw a graph to show the reward, but remember that the y-axis is still the reward for the odd player, and then now the x-axis is y1 because we are going to talk about the column player. So this is the row's reward if the row picks one finger, and then same as before, we substitute y2 with 1 minus y1 because the sum of y1 and y2 must be 1, and here's the equation, and that corresponds to the line AC. So that is the expected reward for the odd player if the row player picks one finger. And then if the row player picks two fingers, then the expected reward is the line from D to E. Okay, so because this is the reward for the odd player, and then with respect to this x-axis is the strategy by the column player. So the odd player will always try to maximize the reward for the row player, right? So this will be the line that happens. That will be the line that shows the reward for row player with respect to any strategy that the column player plays. Again, for example, if the column player plays this strategy, this value of y1, then obviously the row player will pick to put one finger because it is more beneficial for the row player, right? Because if the row player plays two fingers, then the reward for the row player will become lower. So, and then same here, if the column player played this strategy, the odd player will pick two fingers because it gives row player a higher reward than if the row player plays one finger. Okay, so if the column player knows that this V here is the reward that the row player will receive, the best that the column can do is to minimize the reward that the row player will receive. And that minimization happens when the column player plays the strategy of y1 equals half. Okay, so I will give you two questions to check your understanding on this topic. I will give the pause on the video to give you the time to read the question and think about the answer. I will give you the answer after the pause on the video. Okay, so here's the graph that shows the expected reward for odd player with respect to the strategy of the odd player. Now the statement says x1 less than half means that odd player seldom puts out one finger, or in other words, too often putting out two fingers. Therefore, the even player may take advantage by putting out two fingers. Is this statement true or false? The answer is true. So x1 less than a half is somewhere there in the yellow arrow. It means that x1 is smaller than x2. Odd puts out one finger much seldom than odds puts out two fingers. So we can see from the graph, if this is the case, the column player knows that the odd player often puts out two fingers. So if odd puts out two fingers, even player will also put out two fingers, such that the sum of 2 plus 2 becomes 4, and it becomes the advantage of the even player. Okay, you can see that if x1 is less than 12, the even player will pick this strategy, picks two fingers, because 2 plus 2 equals 4, and it will become the advantage of the even player. That makes sense, right? If you know that your opponent, the odd player, often plays two fingers, then you just play two fingers too, because 2 plus 2 is 4, and you will win because you are the even player, right? So the optimal solution says that The strategy should be balanced between x1 and x2. You should not play too much one finger. You should not play too much two fingers as well. You should exactly place half and half for one finger and two fingers if you are the odd player. Now the second question is about the column player. If y1 greater than a half, it means that even player often puts out one finger, or in other words, too seldom putting out two fingers. Therefore, the opponent, the odd player, may take advantage by putting out two fingers, as shown by the line on BC segment. So this segment BC. Is this statement true or false? The answer is false because the line segment should be BE. Okay, y1 greater than half is somewhere in this yellow arrow. It means that this even player puts out one finger very often. If the even player puts out one finger, then you know the odd player will take advantage by picking up two fingers, because 2 plus 1, the sum is 3, and the odd player will win. So that is shown by this segment BE. Okay, and again, this is logical. If even player plays one finger very often, then you as the odd player, for example, you know that you can just always put out two fingers to make the sum 2 plus 1 equals 3, and you will win. Okay, so that is how we find the optimal strategy for the game that has no saddle point. In the next video, I'm going to talk about domination. So see you on the next one. Thank you.